So, before I go on, just flicking back to the previous workshop's content. So I think last week most of you got lights. The people who were here got light sensors working. So hopefully we don't need to go over that too much again. But that was essentially just using our analog inputs and a potentiometer to create variable resistance that we could measure the voltage across to best give us readings back from our light sensors. Now, we did attempt to, I guess, look at RGB LEDs as well. So we went all the way to, where was it? Went to this kind of stage where we looked at, I guess, a little bit of how to control an RGB LED, how the configuration works, and hopefully enough of you got like the RGB LED flashing different colors. So just to go back, if you guys do want to continue with the color sensor, but it's a decent sized sort of project, so I won't spend too much time on it today, but essentially what we did have, the principle I think a few people got confused with last time was that they assumed that the light dependent resistor was the one that was detecting the color of the RGB LED. Now that wasn't the case, that wasn't the point of the color sensor, because we're not measuring the color of the RGB LED. What we're doing is we're measuring the amount of light reflected from an object, another object that the RGB shines onto, and that amount of reflected light for each color is picked up by the light dependent resistor. The light dependent resistor can't tell color on its own. So what we do is we shine a red light, a green light, and blue light sequentially, or in whatever order that you want, to determine how much of each color is being reflected, and from that we can infer what color the object is. So you guys are able to do that if you want in your own time, which is essentially just setting up the circuit and determining what sort of color is reflected the most, or if you compare it to say like a white background, what color is noticeably like more reflected than the others if you consider like a white piece of paper as a sort of a calibration state. Anyway, so, and the other thing that we briefly looked at is ultrasonic sensors. I think we'll be doing a bit more of ultrasonic sensors today, more so. I'll be spending time on that because we might be able to do some cool stuff where we get to hook up an ultrasonic sensor to our Arduino and give us feedback to control the angle of a servo, which I think is really interesting. All right, so we'll go back to workshop number 5. Okay, so just a few announcements before we begin. For those of you doing Eng 1000, we've got a special opportunity for you guys, which is in our next hackerspace coming up next Monday from 5 p.m. In our hackerspace room in Electrical Engineering 319. We are doing consultation for all Eng 1000 students. So if you're keen to get ahead and get your project tested or get some more parts or get some advice, it's a good place to do it. We'll also have the Elect Eng test track up and running there. So if you're doing the Elect Eng 1000, that's actually located in our hackerspace, somewhat by coincidence, but we'll be having it go there. So you guys have access to the track from 2 to 5 p.m. and then we'll continue having access open during our hackerspace from 5 p.m. until about 7 or 7:30. Other than that, our unmanned aerial vehicle team and our ground vehicle team have just recently kicked off. So we're going to get those underway gradually for the rest of the semester and pick up the pace over the holidays. So if you're interested in either being involved in building like a really solid ground vehicle platform that is autonomous, has things like GPS, it's like about like 80 centimeters to a meter in length and you can drive around campus. Or if you're interested in competing in the outback UAV challenge. Those teams are brand new teams which are kicking off at the beginning of this year. So check out our website, our Facebook group. You can see links to where to get involved, where to put your name down. You don't need necessarily any experience to join those teams. All right. So yeah, we don't have YouTube of last week's content, but we do have those Google links. But you can find those in our Google Drive as usual. All right. So I think the first thing we'll do today is servos. So now there's a lot of information in these slides that Austin, who's sort of my assistant for the workshop, has kindly put in. I won't necessarily be following the slides exactly as they go, but there is a lot of information there to refer to. So essentially, all of you have got a servo in your Arduino kits. So if you've got an Arduino kit, or if you don't have an Arduino kit and you want to borrow one, which we are able to do today, then you'll have that servo which we can play around with today. So a lot of people don't actually understand what a servo does. So what a servo is obviously it's a type of motor, but what it does have on board is a controller which enables a precise setting of angle. That is, you can adjust what angle sort of the axle goes to. It has a 180-degree range of motion, which is common to most servos. And within that 180 degrees, you can write to it from an Arduino and choose the angle you want to go to. So servos are generally speaking good in applications that involve like arms that have to rotate or steering or high torque applications. So whenever you're using that kind of range of motion. So we've got 3 wires that come with the servo. We've got our ground wire, which is brown or black, our 5-volt wire, and our signal wire. So what happens is the Arduino will send a pulse signal, depending on the, I guess, the phase of that pulse signal, or the phase width, it will adjust the angle based on that. Now, there's plenty of information in the Arduino libraries on how to do this. For massive servos, and as I've explained to some of you, for a lot of gear motors, you can't power them straight off the Arduino because the Arduino doesn't provide enough power. But for these plastic servos, you certainly can power them straight off the Arduino. So using your jumper wires to plug in the red wire into the 5-volt port and the brown wire into a ground port on the Arduino, any ground port doesn't matter, and then attaching the signal wire to one of the digital pins on Arduino will enable you to control this servo. So in terms of how this works, there is a Servo library embedded in Arduino, simply servo.h. So we create an instance of our servo in setup. So like the keywords like integer or float or variables like that kind of works the same way when you're creating an object. I won't go into too much detail why, but essentially you have capital servo, and then you have the name of whatever you want to call your servo, and then there's that you put that in before void setup so that it can be globally accessing all functions, presuming that's the way you want to do it. And then, given the name that you give to that servo, there's a bunch of functions which you can use with that servo, including to initialize it, you do whatever you call the dot attached and the pin number, which you're connecting the digital sort of input of your servo into. And then after you've done that, you can then simply write an angle to it. So that is the sort of key 2 functions are attach and write. If you do want to use that pin like multiplex for other things, you can detach the servo just by using detach instead of attach after you have attached it to a certain pin. But yeah, all the functions are in there. So the angle is in degrees, and it has a range of 0 to 180. Sometimes at the very extreme of the angle, but because of imperfections in the servo, it may twitch a bit. So if it's less than 5 degrees or greater than 175 degrees, you might find it has unexpected results. But generally speaking, it will be able to write that full range of 0 to 180. So this is an example of how you might use a servo. So we've included the header file. We've called the servo my servo, and we've attached it in setup pin number 9. And then we've got a simple sweep function. Now, I believe that this is actually the example code that is currently available in the Arduino library. If you open up Arduino, and you go to File, Examples, you'll see a already included drop down called Servo there, and the one that we want to start with is sweep. So the first thing we'll just be doing is making sure, now in this particular program, it's attached to pin 9, but just see if you guys can get your servos, your Arduino's connected, your servo's connected, and your servo's just going back and forth with the default program. The extension of this will then be to use the feedback of the sensor or potentiometer to control the angle of the servo. So you need to jump the red wires and white wires. Red wires. Oh, so yeah, that has to go 5 volts. You don't need a red wire. So the red wire is 5 volts, ground is ground, and the orange wire is the wire which goes. Also, before you guys today, we've got some of our car kits here, which have got batteries, motor drivers, and are able to drive around. So when we get on to the content on H bridges, we'll give you guys the opportunity to actually program one of these cars if you want. You've got wheels in here, so you can have a chance of understanding not just motor control, but I guess how to control motors to make cars steer in different directions. And if you are really good at attaching, say, your own sensors, you might be able to get the car to drive around autonomously and say use obstacle avoidance with an ultrasonic sensor in your kit. So hopefully that's what we'll get you around to doing today. So yeah, obviously the way the sweep program works is that it's writing an angle and incrementing and decrementing that angle in cycles. Uh, so if you have a look at it, it moves 1 degree every 15 milliseconds, which means that it goes through 180 degrees in a bit under 3 seconds, essentially. I believe. Yeah. How's it going? Yes. Find a computer. Yeah. Yeah. Great. We're just going. Huh? I think it's great. Alright. So yeah, you guys can also play around with the speed of the servo sweep by adjusting the time. The servo can go reasonably quickly. It will probably do 180 degrees. If you can just go right from 0 straight to 180, it will do it in probably about half a second or less, maybe even 0.3 of a second. But obviously, yeah, if you write it really, really quickly like that, it uses a bit more current draw on the Arduino, but these servos can handle it. Just be aware you don't want to stress the servo too much. Like, if you hold the servo horn, the little sort of white attachment is called the horn. If you try and force against the servo, you can break these servos. These servos aren't designed to be deadlocked with force. So just be aware of that. That's a separate project. What if it stops up there? All right. So after you guys have got those servos working, as I said, I'm not going to follow along precisely with the slides today, but this is a good task as a refresher for what we did last week. But you guys don't necessarily have to use a light dependent resistor embedded light level. But what we do want to see is using the servo to deliver some kind of feedback on one of the sensors. So it's up to you whether you want to hook up an ultrasonic sensor, a light sensor, a potentiometer, even like a switch would work. But see if you can modify the program that you've got, or if you're confident enough to start your own program and get the servo to respond to external input. So this will mean that you'll need to obviously, if you're directly translating ranges of, say, sensors or things like that, you need to make sure that the input to the servo is between 0 and 180. It doesn't go outside that, and it's an integer as well, but you'll be dealing with integers most of the time.
Are you guys
So yeah,
okay?
see if you can get the servo
I think that I
sweep
joined you guys.
anymore, but actually to respond
Yeah, this is you guys.
to something.
You build yeah, yeah, we do some of that. And we teach people how to use these things and teach them how to print, 3D printing. Yeah, stuff like that. Yeah, pretty much just making things. Like these things every week. Yeah. Here or upstairs? 12:30 to 2. No, it's never too late. Each week isn't attached to the week before. Maybe some basics you need to know, but you can always help you catch up if you want to. Especially now in the semester, everyone's listening. Well, we have, did you join the website as well? If you join the website and sign up to the mailing list, they can send you something. Do you have? Do you have your computer open? Yeah, sure.
All right. So I'm going to write a sample solution of responding to an external sensor using an ultrasonic sensor. To give you guys, I guess, an example of what you could do. So I'm just going to open two things. Let me just change preference. This is too big. Maybe 36. Okay. Now, if you guys did want to install and use the ultrasonic sensor, you will need a library to go with it. So I'm just going to quickly cover how to add libraries to your Arduino environment. There's information on how to do this online, but I'll show you guys now. So I probably should have shown you guys this before, but in the Create Google Drive folder, you'll find a folder called Sales Parts. And in Sales Parts, you'll find another folder called Part Libraries. Now, part libraries include some of the Arduino libraries to use with some of the modules that we send. So, for example, we've got our LCD display driver, we've got an IMU library, we've got our ultrasonic library, we've got our RF library in there. So, these are all sort of open source, but yeah, what you can do is you can simply download the zip file of the library. Hopefully that will just appear somewhere. Save file. Cool. And then in your Arduino environment, you can then go to Tools, Sketch, Import Library, Add Library. And then hit on the zip file that's there that you've just downloaded. Hit Open. And now I should have imported the library. So if I go to Files, Examples, it should be there, New Ping. Yep. So New Ping is the name of the library for our ultrasonic sensor. You don't have to use it today, but you can if you want to. I'm just going to open up New Ping example. All right. So we've got Servo on the left, New Ping example on the right. I think I'm going to combine the two of them. So what I'm going to do is I'm going to ignore the serial print information. But what I will do is we will, let's see, include these three lines, and then maybe put instead of max distance 200, put max distance 180. So I'm going to copy and paste that in there like that. Then I'm going to insert the instance of creating the ultrasonic sensor up near my servo. So we've got new ping sonar up there. And now there should be a function which you can use called read centimeters. Let me just open it up. I'm just going to go quickly back to the previous workshop because we had some good information there. Where is it? Ping underscore centimeters. So ping underscore centimeters will do the trick. So you can simply write, oops, wrong Arduino environment. Something like that would do it. So just what I've got on the left. So what this program will do, and notice that the number is in centimeters and I've set my max distance to 180 so I don't exceed the range of the servo. But, I forgot to include the most important thing, which is I've got to include yeah, all right. So that code as it is compiles. So after we've imported our libraries to the Arduino environment, I'm including Servos, I'm including UPing, I'm defining the trigger pin and the echo pin and the max distance. I'm initializing the servo, I'm initializing the sonar sensor. And then I am writing to the servo the value from the sonar sensor. So I'll just zoom out of that a bit so you can see what I'm doing. So yeah, hopefully you can see most of the program there. So including servo, including new ping, defining a few variables. None of them. Oh, none of them? No. This is just the best function to use for new ping. It's just ping underscore.
Sounds interesting.
Yeah, yeah. After downloading it, and then yeah, just doing and then yeah. Define echo pin, max distance, and so to connect the sonar sensor up, for those of you who are interested, there is a lot of information in our Arduino Workshop course slides. So hopefully, I'll just connect that stuff to an Arduino and we can see what happens. Yeah, it's going to be fixed wing for sure. I thought it's 3x3. Yeah. Yeah, nautical mile is just really annoying, but it's a bloody big area, and it's you got to find it within a time limit, and sponsored by Boeing. First person to complete the challenge gets $50,000. Like, It will go. Yeah, we'll still. I think it's a pipe dream, but if we got it, that'd be sick. Just won't think about it yet. Okay.
Someone managed to blow off parts when
How?
I don't even know. It's like it's not connecting to the thing and it's not showing up on the COM port. And I'm like, and I was just like feeling different parts of the Arduino, and then I found it and it was just like hot. And you plug it in and it turned on and they're like, oh, it's gone. What does this code do?
It's meant to be controlling a servo as based on
That
distance.
looks like it's going on. That looks like it's in backwards or something. It's just shaking.
Yeah, let me just quickly check.
I just remember whenever my servo is going space like that, it's because I put it in backwards.
Oh, I haven't put it in backwards.
Yeah.
Why is this not working? Alright, that's better. So turns out my servo was broken before, but for those of you who are interested, I have a working servo feedback from Ultrasonic Sensor set up ready to go. That's really cool. Yeah.
I did it with a piezo buzzer. So the closer you get, it just buzzes more.
Oh, really?
Yeah.
Nice. closer, further away. Well, it's hard to get to 1.80 m. Alright. I think we might move on. Hopefully you guys have had some fun with the servos and got them working. Again, if you're working on, it doesn't matter what you're working on, but if you've got any questions, put up your hand. We've got plenty of volunteers that know what they're doing floating around.
Hey, thing, how do I like re-upload?
It's already done.
Oh, so if I just close it, get out of it?
Yeah, so, yeah.
Oh, cool. That's great.
Alright. Alright, so before we go into hooking up an H-bridge, I'm just going to go into the theory of motor drivers, motor controllers. So, unfortunately, these weren't standard in the kits, but we do have, as I said, some of the cars here. So if you want to experiment, even if you don't have the parts, we can do it today. So a motor driver is basically a signal amplifier. So in terms of digital logic, our Arduinos don't have enough current to drive even small size DC geared motors. Anything that draws, over 100 to 200 milliamps, we really want an external system that is able to power and control that. Now, the problem with this is that it reduces the ease at which the motor can be controlled. Well, although it's not that difficult, but a lot of students struggle to get motors to go both forwards and backwards. If you are just turning a motor in one direction, all you need is the equivalent of an electronic switch, which is otherwise known as a transistor. So you can hook up an NPN transistor quite easily in series with the motor, place it in the circuit after the motor though, because it's important actually like what side of the load it's placed on. So you go 5 volts to motor, the NPN transistor with the middle pin of the NPN transistor being your signal wire, and then that goes to ground. And that can control a motor if you just need to switch in one direction. However, if you wanted to go in both directions, which is what any useful robot does, we need an H-bridge. So, what is an H-bridge? An H-bridge is essentially an arrangement of what equivalent of switches that allow us to change the direction of a motor. Obviously, we can't use mechanical switches if we want to control it digitally. So an H-bridge has the equivalent of transistors where those switches are in a certain orientation. So those two diagrams demonstrate how current and hence the rotation of a motor is reversed depending on how you control the H-bridge. Now, an H-bridge like this chip that we have here, which is what's attached to the cars, has that arrangement for us and does the logic for us a little bit. So we have our power supply which goes to our H-bridge, which is indicated by the orange wires. These ports are labelled on the underside of the H-bridge. You've got your voltage in and you've got your ground. You've also got your terminals to your motors. So motor 1 on one side, motor 2 on the other side. And then you've got your signals to your Arduino. How this works. Essentially, to get current going through a motor, we need a voltage difference across that motor. This means that we need one side of the motor to be written to as a high voltage or a high level, which is 5 volts in the case of an Arduino, or more depending on your power supply. And the other side needs to be written to ground. So there are, whilst there's 2 motors, there's 2 outputs for each motor. So there's like an output 1 and an output 2 for motor A, for example, and an output 3 and an output 4 for motor B. So the Arduino then, you can either have 4 outputs coming from your Arduino, inputs coming from your Arduino to control each of those outputs directly, or you can halve the number of inputs by adding some inverters to the system. But generally speaking, because we like to turn our motors on and off under easy control, the inputs are set directly with the outputs. So that means to control motor 1, we would need to set output 1 to high and output 2 to low to spin it one direction. And vice versa, if you want to spin it in the other direction, you put output 1 to low and output 2 to high. Now this is presuming that you want to go full speed in either direction. Obviously, we have the ability to analog right pulse width modulation, and that can control the speed of motors in both directions. So setting one of the pair of pins to high, the other one to low, will drive the motor in one direction. Swapping those around will reverse the motor. And we can use the analog right to control the speed of the motor. So instead of digital writing one of the pins to high, we would analog write it to whatever value between 0 and 255 we so choose to imitate a variable voltage being sent to the motor. Another way that you can, so as I said before, another way you can control your motor, power your motor, is from a transistor in the kits. We have given you an NPN transistor, it's BC547, I believe. You read the part number on there. If you just want to control your motor in one direction. Otherwise, for those of you who are interested in controlling motors, don't have the parts, or want a car to experiment on, put up your hand. We can lend you a car for the workshop that works, and you can have fun programming it and essentially trying to spin your motors up. So basically, it has two settings for that slide. So you include your servo H. There's also an example file and you go to servo, which is now on you should myservo.write write is in right, not right hand, right, W-R, not capital, right, yeah, and then put open bracket, sonar, dot, in, underscore, underscore. close bracket, close bracket. Open, close bracket. Yeah, like that. And that should work. So what we're doing is we are but yeah, so what we're doing is we're writing, so we define something called sonar, and there's a sonar centimeters, which returns the number of centimeters as detected by this thing. Yeah. So presumably you're able to library. You know which comfort it is?
So H-bridge can work fine with 9 volt, right?
Yes.
Okay. And like, is 9 volt enough to drive 4 motor? If you put two on
4
each
motors.
console, yeah, cause is it like
In series or in parallel?
unlike so?
One 9 volt battery, 4 motors, and 9 volts. But a 9 volt battery is providing 9 volts of current. Like you have like 6 AA's, that would be better. One 9 volt battery is like one motor. Yeah, really, yeah. One motor, yes. 2 motors, I mean, it'll draw it. The battery will not last. No, the enables already shut off. Don't worry about it. Yeah. Has your enrollment open for next semester yet?
Friday 4 p.m. I got an exam Friday 3 to 4. I'm trying to finish it early, get out.
My enrollment opened yesterday. I'm still figuring out like my thesis, like what I'm doing. I'm probably going to extend my degree by 6 months, finish at the end of next year.
Yeah.
Because I really don't want to start thesis next semester.
Just gonna prolong it.
Yeah. Gonna prolong it and take it easy for my thesis because I think the thesis needs a bit of planning, and I have not planned, and I'm going away in it's like break. I'm not gonna have something come back and just like, oh yeah, thesis, right?
What do I want?
Exactly. That's just like a risk.
You got nothing in mind yet.
Quite confident, but I'm not sure what. Yeah. I mean, I have thought about a little bit, but not enough.
Yeah. It's like everyone's in the same boat.
Yeah. So, for those of you who are interested in what controlling the motor looks like, now there is a Boeing setup before this that simply just initializes the pins to output. So don't forget when we're using digital pins as outputs, you need to put a pin mode first. Likewise, the same with inputs. We're using an analog pin from a potentiometer. And if you guys remember from a couple of weeks ago when we learned about map function, we're mapping input from a potentiometer to control speed from the motor. So what this does is it maps it to a range between -255 and that enables us to write backwards and forwards. So if we do some logic that analyzes if the potentiometer is reading greater than 0 or if the speed is greater than 0, and then we digital write one of the pins to low and the other pin to the value of that will be greater than 0. Likewise, if it's the opposite, then we analog write the negative of the speed, which is going to obviously be the negative of a negative number, making that number positive again, and it will be between 0 and 255. And we write the opposite of what we did before. So that's an example of how you can connect up a potentiometer to an 8th bridge to control a single motor. So pin 1 and pin 2 would be for the two outputs for one motor.